Welcome to Experimental Hall C at Jefferson Lab. Hall C is 150 feet in diameter and 60 feet tall. It was the first experimental hall to begin taking data at Jefferson Lab in 1995. During experiments conducted in Hall C, electron beams from CBAF enter the hall through an elevated pipe and are directed into an experimental target. A target might be any gas, liquid, or solid, which could also be polarized or cryogenically cooled. Inside the target, electrons collide with individual nuclei and the subatomic particles inside them. Two high-momentum spectrometers, or detector systems, capture and measure the particles that emerge from these collisions. Experiments conducted in Hall C typically focus on studies of the properties of the subatomic particles that build our visible universe, including atomic nuclei, protons, neutrons, and quarks.
Hello, everyone, and welcome to Bite-Size Science, Jefferson Lab's virtual lunchtime seminar series. I'm Szumila-Vance. I'm a staff scientist here at Jefferson Lab, and I'm excited to share with you today about what is going on in the proton. Our previous summer series have focused on topics ranging from accelerator science and technologies to machine learning and artificial intelligence. And today I'm going to give you this talk in the context of nuclear physics, which is the heart of what we do here at Jefferson Lab. This is a recording of a previously broadcasted live presentation, and so we had some audio issues on the first one. So this recording, I will answer the questions that were posed from the live broadcast at the end of my presentation. So how can we describe our universe? We want to know how we can take the fundamental building blocks of what we know that makes up all of matter and describe the big things that we see, whether I'm just talking about the computer in front of me or I'm talking about the stars in the sky. And so at night we walk outside and we can admire the stars and see planets and kind of stand in awe of the universe that we're in. But what's really fascinating is that all of the building blocks of matter that make up you and me and everything that we see were all created right at the moment of the Big Bang. So while it may seem that if we actually want to describe our universe and figure out, here we are standing on planet Earth and on the Milky Way galaxy, and put that into the context of the stars, that we would need to look outward, you could imagine scientists who look through telescopes. But here at Jefferson Lab, we actually look inward. We look at the building blocks, the very fundamental, indivisible type of particles that make up matter, to figure out how we can explain and put together these pictures of our bigger universe. So here at Jefferson Lab, as I stated, we look inward to understand the things outward. So studying the proton gives us insights basically to describe matter at all scales. So shown here on the far left is sort of an artistic picture of what you could imagine a proton to look like, which we now know is made up of things, even smaller particles called quarks. And we know that if we can have a good description of things like protons and neutrons and these types of things that are built out of quarks, gluons, then we could describe something even bigger like ourselves, the Earth, the sun. And this picture in the center is the Hubble Deep Field picture, which you can look out and see in deep space, lots and lots of galaxies. And everything that you see is composed of these protons, and which are composed of these fundamental building blocks. So we look at matter at all scales to try to put together this really coherent picture and description. And the important thing about asking these deep fundamental questions is that they can also have benefits for us in our everyday lives, besides just answering these big important questions. For example, here on the right is a picture of proton therapy, which is a newer technique that was basically developed when we were better able to understand protons as a means of fighting cancer and to preserve surrounding good tissues within our bodies. And so this is just an example of how these types of pushing ourselves to new technologies to answer these fundamental questions has good implications for other experiences in our life. So let's take a step back for a moment, and we'll just ask, how is matter organized? I keep talking about matter, and so I'll just start with something really simple and tangible. Of course, this is the bite-sized lunchtime series, so let's just start with an apple. And so, you can hold an apple in your hand, and that's something that you can see with your eyes, and, photons bounce off of it, you can see it. And so if we were to go one step smaller than that, what makes up the apple? Of course, you have molecules. And so you might be familiar when people talk about molecules with things like if you're talking water, you can talk H2O, right? So two hydrogen atoms and oxygen atom, and they're together and they make up a molecule of water. And so the molecules, describe basically the kind of chemical composition of what it is that you're looking at. And so, as I've already kind of alluded to, even smaller than that then is the atom, because you have, in water, you would have two hydrogen atoms and oxygen atom. And so here we have the atom. So the atom is made up of things like electrons, which you see here orbiting the nucleus, which is at the center. And so the picture of the atom here on the slide is a little bit misleading, because the atom is really, really small and very difficult to sort of comprehend in our everyday, life experience. So let's put this into perspective. If you were to look at your pinky finger, your smallest finger on your hand, then you could line up 1 billion atoms across the top of your finger. So they're pretty small. And then if you could expand sort of the atom, so to speak, to say the size of a soccer or a football field, then the actual nucleus of that, so the center of it with the protons and neutrons, would only make up about the width of your pinky nail. So pretty small. And so we know now that the nucleus itself is made up of protons and neutrons. And it's the nucleus that also tells you what type of element it is that you're looking at. So what do I mean by that? Well, elements are defined by the number of protons in the nucleus. So maybe you're used to, or maybe you just remember from chemistry class that, we have the periodic table here, which contains all of the known elements in the universe. And these elements are described, in order with a number, this atomic number that you see here. So I've taken the carbon off to the side, and you can see that this atomic number is what tells you how many protons are in the nucleus of that element. And so, here in the carbon, for example, we know that we have 6 protons. So we can have various numbers of neutrons. That doesn't change necessarily what the definition of the element is, but that's just one characteristic of how protons tell us what type of element it is that we're looking at. But that's still not quite the full story. So we know that we have protons and neutrons which make up the nucleus, but even smaller than that, we know that protons and neutrons are made up of the building blocks of matter that begin with the quarks and gluons. So the quarks are what are shown in the colorful sort of spheres here at the bottom left side of this slide. And these quarks interact with each other through gluons, which are mediators or carriers of the strong force interaction, which is what holds these quarks together. And so even that picture, as we explore what this picture looks like of the proton being composed of 3 quarks, we know that picture actually still gets even more interesting when we look at even finer resolutions. But I'll talk more about that later. So let's talk about the proton. So the proton is a really special particle because it's the most stable particle that we know of, basically, that's composed of other particles, has an incredibly long lifetime, and apart from the proton, all other particles that we know of basically decay. So what's really interesting about this is that basically every proton that we know of was created just a millionth of a second or so after the Big Bang. And so the proton we also describe as a baryon when we talk about types of particles. And all that the baryon means, since you're probably not used to hearing about this, is that it's made up of 3 primary quarks. And so we can have different types of particles that might be made up of 2 quarks or 3 quarks, but here we're talking about a proton, which is made up of 3 primary quarks. And additionally, a proton is characterized as having a mass. And so while the mass listed here is super teeny tiny, but you can imagine that things, very big objects like even you, me, the sun, our Earth, the mass of those big objects is attributable to the protons and neutrons that make up that object. So the protons carry this mass, and then additionally, protons are characterized as having a positive charge. So it's a +1 charge, electrical charge is what I'm talking about. And so we know that sort of as we look at the proton, you sort of imagine that it's the single object, and then we look a little closer and it's made up of these quarks and gluons, and the picture just gets more and more interesting as you look closer into this particle. Now, I told you that protons have mass. So when we stand on a bathroom scale and weigh ourselves, we're trying to measure our weight, which is proportional to our mass. And so now if we were to take the proton and put the proton itself onto a scale, and then we take out those 3 quarks that make up the proton and put those on a scale, we learned something really interesting, is that the quarks themselves, these 3 primary quarks, only make up less than 1% really of the mass of this proton. So what's going on here? Well, we know that there's also gluons inside of the proton, but the gluons are massless. They don't have any mass. So where is all the mass of the proton? It turns out that Einstein actually gave us a clue. He told us, of course, that there's a relationship between the energy of an object and the mass of an object proportional to the speed of light squared. So the actual proton mass has to account for the fact that you have 3 quarks, 3 primary quarks that make up the proton. But these quarks themselves are relativistic particles with they're confined to the proton. They carry a lot of momentum and energy inside of the proton. So we know that if you want to calculate the mass of the proton, you have to not only include the rest mass of these 3 quark particles, but you also have to include all of that energy and momentum that they are carrying inside of the proton to calculate its mass. And actually, it turns out that if you include all of that, that does account for about 99% of the mass of the proton. So, in fact, there's so much going on in here that the gluons, which are shown as sort of the squiggly yellow lines here connecting the quarks, also are splitting, and you have quark-anti-quark pairs that pop in and out of existence within the proton. So I also told you that protons have charge, electrical charge, and so they're made up of, for example, 2 up quarks and a down quark. Not very creative names, but the up quarks themselves carry a +2/3 charge each, and the down quark carries a -1/3 charge. And so if you sum all of that, then you get your +1 positive charge for the proton. And this leads to types of experiments. This is on the right side, you see an artistic picture from a recent Jefferson Lab experiment, which is really exciting because you can basically calculate what the radius of space is that sort of is occupied by these 3 charges within the proton, these 3 quarks that make up the charge. You can measure kind of like a charge radius is what they call it. And so they were able to measure that here at Jefferson Lab with really, really high precision. So we know a lot of things about the proton, and the craziest thing is that we actually can't see one with our own eyes, like as if we could just dial in a microscope and just see a picture of it, even though we can draw very nice pictures of what we think we are seeing. So I sort of liken it to if I were to give you this clock and ask you to tell me how this clock works. You could work out some rules about the clock, right? You could determine that the hands always move in the same direction, and that the smaller hand moves from number to number when the longer hand moves all the way around the face, and that you could work out that the shorter hand, of course, moves around the whole face of this clock in between sunrise and sunset, for example. And so you could work out some rules too. You could even predict what it might do next, and start to describe those kinds of things. And that's sort of like developing theories based off of observations. Now, if we were to drop the clock on the ground and it broke open, then you would realize it has gears inside of the clock. And so if we take those gears, then what we actually really want to do to understand the theory and to understand, in this case, the proton, we want to take those gears of the quarks and gluons and we want to assemble them into a really coherent picture and framework to describe the proton and and how it works, and then hopefully take that picture and describe it to even bigger forms of matter, the bigger nuclei. So we want to study the proton structure is what we really want to do. So just imagine trying to resolve something, for example, in this dark tunnel. If you were standing before this dark tunnel and I told you that there's a statue in there and we want to see it somehow, but the only tool I gave you to see it with was this ball. So if it's a sufficiently small enough and bouncy ball, then you could throw it down this tunnel, and you could at least first you would probably trace out where this object is, so you could kind of see the shape of the object. And then if you could calculate every single angle and the force at which it returns to you after you're bouncing off of the object, you could resolve what this object is. So in this case, I put in The Thinking Man by Rodin. Now, you would probably need a very small ball to resolve, for example, the finer details of his face and hands. But this is sort of similar to basically what we're doing here at Jefferson Lab with the proton, is that you can replace your ball with an electron. So we have an electron beam. And you can replace your tunnel with your proton, and your quarks and gluons are your thinking man. And we can interact with the proton as well as the quarks and gluons to determine what this picture looks like. So here at Jefferson Lab, we have an electron beam that can generate up to 12 GeV beam energy, which circulates underground. This is an aerial view shown on the left side. And we have 4 experimental halls, which is really just where the beam can come into those halls and interact with some kind of target material. So in the video you saw just before my presentation, you saw the inside of Hall C, which I've shown here on the right. And you have Waldo at the very center for size. And so right above Waldo's head, you can see in the center is sort of like a tin can, and that might contain your target material, which might be a hydrogen proton, or it could be something bigger, like a foil of carbon or some kind of other material. And so the electron beam would come in and scatter with that, interact with that material, and then you could detect the particles in the spectrometer arms that you see on the left and right, the kind of big blue, yellow, and green-yellow structures. And those can pivot around on tracks depending on what it is you want to study. So basically, Jefferson Lab is really just like a big microscope. So we can tune the microscope with the electron energy and momentum transfer to determine what it is that we want to study. And we can look at, for example, the whole proton. We can also look at basically the proton. We can start to resolve the things inside of the proton, these quarks. And we can even dial it in even further to start to look at this sea of quarks that are around our 3 primary quarks that pop in and out of existence. And so at Jefferson Lab, for example, in Hall C, in a recent experiment, we were using the electron beam to knock, essentially, protons out of the nucleus, and then to measure both the electron, the scattered electron, and the protons that we kicked out of the nucleus. And we were, in this case, looking for protons that had quarks inside of different types of configurations inside of the proton. But you can also measure things, for example, in this type of scattering, which is elastic scattering. You can also measure things like what is the probability that the proton survives to make it outside of the nucleus. So when we talk about protons inside of the nucleus, we're talking about protons surrounded by other types of protons and neutrons. And protons in this instance are a little bit like people, so that if they're far apart from each other inside the nucleus, they'll have no interaction. But when they start to come near each other, they may exchange particles between them. And this is sort of an attractive action between them, which is what helps to basically bind the nucleus. The protons and neutrons binds this nucleus of the atom together. And at very, very short distances, if you could imagine a person standing too close to you in an elevator, they strongly repel each other. And so it's actually, these actions are all kind of spillover type of effects from this fundamental quark-gluon actions inside of the proton. And finally, we can also look at things like, if we want to see the inside of the proton, we can break up the proton to see what comes out. This picture here shows a high energy incoming electron scattering with an individual quark, and you can measure the scattered electron and what comes out of that to determine, for example, how the quarks are distributed inside of the proton. And we can also study basically the structure of how those quarks are arranged inside the proton. And things that we've learned, for example, are that a free proton floating around in free space is different than that of a proton inside of a very heavy nucleus with lots of other protons and neutrons. And so we hope to understand basically how these pictures emerge from fundamental interactions. So I hope I've given you a sense of how we can study the building blocks of matter to get a better sense of how we would describe our visible world around us. And that's really the goal here of Jefferson Lab, is to build a coherent program with our 12 GeV beam to study not only the proton and in great detail, and then to start to, as like a very ideal laboratory to study quarks and gluons and their fundamental type of interactions, but then to better understand how protons from those interactions are changed inside of nuclei. So at this point, I would like to thank you for listening to my presentation, and I will turn it over to our moderator to ask some of the questions that have been submitted.
Thank you, Holly, for all of that great information. We have some pre-submitted questions and questions that were asked during the original video. So we'll go ahead and start off with some pre-submitted questions. The first is, why do you believe that it is important to study the proton?
So I mentioned that the proton's really special because it's stable, but it also, because I guess what I didn't emphasize maybe was that one can't really see a free quark. Quarks have a special feature called confinement, where we always find them confined inside of other particles. There's always at least two quarks, quark-antiquark pairs together. So the proton is really special because it's this stable particle in which we know that these quarks and gluons, exist, and we can basically use it as a laboratory to study those fundamental building blocks of matter.
Okay, great. So do you believe that we will ever see a proton during our lifetime?
So it's not a question of technology or capability, I guess. It's for example, when we see things because light photons bounce off of objects, and our eyes are these sort of perfect particle detectors for seeing photons. And so, we use visible light bouncing off of objects to resolve what they are, what we're seeing. And so, a proton is far, far smaller than the kind of visible light range that we would use to see an object. So we use other tools basically that we can then infer what it is that we're seeing from the proton. And so here, that's sort of why, in a sense, that Jefferson Lab is sort of this great microscope kind of device, because electrons are really small particles, and we can use them to therefore sort of resolve the proton.
Okay. So why is Experimental Hall C the place you chose to conduct your science at the lab?
Yeah, so each hall has different capabilities. Hall C has the ability to get really, really high intensity beam, probably the most intense beam at the lab, which means it's the most number of sort of electrons coming in at really high rate into the hall. And so we can measure these kind of rare type of reactions, things that, have lower probability of occurring, but we can measure them with really, really high precision because of the detectors that are there. So they look at a very small region of space, basically, to look at where particles are coming off from these reactions. So in Hall C, the experiment I was recently working on, where we were looking for protons with the quarks sort of we were looking for protons where their quarks were like overlapping each other inside of the proton. And that's not really a very easy thing to measure. And so we needed very high intensity beam, and we needed to have very clean way of detecting the protons coming off of that. Other experiments throughout the lab, though, have complementary types of science going on. So they can look at protons inside of other nuclei. They can measure wider regions of space of where the particles are coming off from such an interaction. But they all sort of, the hope would be is that all of these different ways of measuring would all contribute to one picture sort of the proton.
Okay, and it looks like we have time for one more question, and that question is, how does dark matter affect the proton?
Yeah, so the protons, for example, so we know that dark matter exists because we've made observations into galaxies, for example, and we can see that galaxies, the rate at which they rotate, we would think that they would just fly apart unless there was some other type of matter that we're not able to really interact with. We can't find any way to interact with it anyways and observe it. So we do know that dark matter does interact gravitationally. So in terms of the proton, then we know that basically dark matter is definitely interacting with the proton gravitationally. I think there's still a lot of speculation about how we can keep looking for it. There's a lot of different ways to look for it, but that's sort of the underlying premise of how it interacts with the proton.
Okay. Thank you for taking the time to answer all these questions. That was super informative, and I'm going to kick it back to you.
Okay, thank you very much. So I want to thank everybody for tuning in today. And again, we have an upcoming talk next week. Actually, it's August 12th, and that'll be live streamed here. So that'll be with Nobuo Sato talking about exploring the world of quarks and gluons. So please, I would invite you to join and to ask questions. Thank you again.